In today's class, we'll learn about quadratic forms, all about quadratic forms. What is a quadratic form? How to represent that in a matrix notation, right? How to reduce a quadratic form into its canonical form, some nature of the quadratic forms, and all those things one by one, right? So this class is all about quadratic forms. Right. Let's see. What is a quadratic form? A homogeneous polynomial of second degree in concerned variables is what we call a quadratic form. Homogeneous polynomial of second degree, right? For example, x square plus 2hxy plus by square. This is a homogeneous polynomial of second degree where a, 2h and b, they're all the coefficients, right? And this is a quadratic in two variables, namely x and y. It need not be in two variables, it can be three variables, four variables, and in n variables in general, right? Now, here is an example of a quadratic form in three variables, namely x, y, z. X square plus by square plus cz square plus 2h xy plus 2g yz plus 2f zx, right? And we can see it's a homogeneous polynomial of second degree. And this is a quadratic in three variables, namely x, y, z. And here is a quadratic in four variables, namely x, y, z, w. And in general, a homogeneous polynomial in n variables, say x1, x2, xn, is given by, I cannot write it in a form like earlier case. I need to write it in a sigma notation. In a sigma notation, it is a sigma bij xi xj, where two sigmas, because one sigma runs for I and another sigma runs for j. And I runs from 1 to n and j runs from 1 to n, right? So now the coefficient bij here is a combination of bij and bji, because xi xj is same as xj xi. So their coefficients together, that is bij plus bji, is what is the coefficient what I have written here, right? Now, issue is how to represent a quadratic in a matrix notation. A quadratic can be represented in a matrix notation as x t x transpose x t a x, where x is a column matrix of variables involved in the quadratic, right? xt, I mean, it's transpose, it's a column matrix, it's transpose. A, we choose always A as a symmetric matrix, and X is a column matrix of variables involved there. Right? Now, a quadratic Q, by the way, a quadratic is denoted by a Q. Q can be written in a matrix form as xtax, where X is a column matrix of variables involved in the quadratic, A is a symmetric matrix, and of course, once X is known, X transpose can be found easily, right? Now, take an example. For example, you take the earlier example, this example, ax square plus 2hx plus by square, and this can be written in a matrix form as it's a quadratic in two variables x and y. So capital X, namely the column matrix of variables, it becomes x and y. Its transpose is xy, and these two coefficients, a and b, will go as diagonal elements, and this coefficient will be split up, right? Now, a quadratic has two types of terms, right? Square terms and non-square terms I call a cross terms, right? These two, x square and y square, tomorrow z square, these are called square terms, and the remaining that we call it as a cross terms, right? The a and b will go as diagonal elements, and this get 2h will split it up into h and h and will be allotted as a non-diagonal elements. So this is how x transpose I'm sorry, x transpose a x. Now we can see here A is a symmetric matrix. Now you take the second example. Now these are the square terms, these are not square terms. Now A, B, C, it goes as diagonal elements. This gets split up, 1 and 2. So it gets split as a 1, 2 and 2, 1 position, a H here and a H there. And similarly, 2, 3 position is split as G and G, and 1, 3 position is split as F and F. Look, this is our X, capital X. That is a column matrix of variables involved in the quadratic. This is X transpose. This is my symmetric matrix. Now, you take this example. This is a quadratic in 4 variables, namely X, Y, Z, and W. And A, B, C, D go as diagonal elements, and the remaining they get split up and they are allotted accordingly. So now we can see A is a symmetric matrix. And right. Now, these are the two results we use. A quadratic can always be expressed as a quadratic can always be expressed as a in a matrix form as xtax, where this y I say it's a coordinate system there, where A is a symmetric matrix, and since A is a symmetric matrix, vice versa, if A is given, I can represent that by a quadratic. Now, two symmetric matrices A and B represent the same quadratic if and only if they are similar, right? That is B equal to P transpose AP, where P is a non-singular matrix. Now, let's see. What is a canonical form? A quadratic which contains only square terms is what we call a canonical form. For example, here, this is in its canonical form. This is not in a canonical form, right? Now, one of the issues is, given a quadratic which consists of both square terms and cross terms, non-square terms, how to reduce a quadratic into another quadratic, say a q dash, which contains only square terms, is what I call canonical form. The process I call canonicalization, right? Given a quadratic q, transforming that quadratic q into another quadratic q dash, which so that it contains only square terms, is called reducing a quadratic q into its canonical form q dash, right? Let's see how. We know a quadratic q can be represented in a matrix form as q equal to xtax. Now, what is the transformation? X, I mean, we are just changing the coordinate system, right? Let x equal to py be the transformation. Now let's see what happens under this transformation. Now our quadratic q, which is xtax, plugging in py in terms in place of x, it becomes py whole transpose into a into py. Now by associative property, I just interchange the terms. Then you know this is y transpose into p transpose a into p into y. Now we know that P transpose into A into P will be a diagonal matrix. Then this becomes Y transpose into D into Y, meaning it contains only diagonal elements, meaning it contains only square terms. This is what I call reducing the quadratic Q into its canonical form through a transformation x equal to P1, right? And right, how to choose P and all those things we'll see later. Right. There are two types of transformations. One is called orthogonal transformation. Another is called congruent transformation or a linear transformation. Now already we know that x equal to py is a transformation which transforms Q to its canonical form. If P is chosen as an orthogonal matrix, then we say the transformation is orthogonal transformation. If P is a non-singular matrix, then we say that it's a congruent transformation or it's a linear transformation. Right? Let's take an example. Let's take a quadratic cube and let's see how to reduce it into its canonical form by a congruent transformation or by a linear transformation. We know that x equal to py is the transformation. Plug in x equal to py. We know a given quadratic cube can be written in a matrix form as x transpose ax. Plug in x equal to py, and then finally it becomes a y transpose or a b into y. Right? Now, let's take an example. Now, here is an example. Reduce this quadratic, which is a quadratic in 3 variables, namely x, y, z, into its canonical form. The question can also be posed as diagonalize the quadratic by a transformation, a linear transformation, and write the linear transformation. Yeah, what is the linear transformation? X equal to p1, right? Once x is known, getting a y is pretty simple job, but figuring out p is important here, right? Or, in a simple words, reduce the quadratic into sum of squares. Whatever. Finally, we say reduce the quadratic cube into its canonical form. So what we do is we'll write the matrix of the quadratic A. We know that it's a symmetric matrix, right? How to write? You know, 3 and y square coefficient is 0, 3, 0, 3, they go as diagonal elements, and these 4, 8 and 8 will be split up accordingly. So the matrix of the quadratic A, which is a symmetric matrix, we get 3, 2, 4, 2, 0, 4, 4, 4, 3. Now, we know a matrix is an altered if it's pre-multiplied by an identity matrix, corresponding identity matrix, and post-multiplied by identity matrix. That is what I mean is, we know this holds good, A equal to I3 into A into I3. I just plug in the numbers here, the matrices. I just substitute the matrices here. Now what I do is, this is what I say a pre-multiplied matrix. This is what I say a post-multiplied matrix. Now, through a bunch of elementary operations, namely elementary row operations and column operations, I reduce this to a diagonal matrix, right? In the process, I need to perform a bunch of row operations and a column operations. What all the row operations I perform will be performed on this pre-multiplied matrix, and what all the column operations I want to perform will be performed on the post-multiplied matrix. And end of the day, this becomes a diagonal matrix. This is my P inverse, this is A, this is my P. Thus, B equal to P inverse into A, P. We know that P inverse into A into P will be a diagonal matrix. We have seen that in the earlier classes. Now, look, now first I perform the row operation that I'm going to perform on this and on this. Right? Next I perform a column operation that I'm going to perform on this and on this post-multiplied matrix. Right? Like that, a bunch of row operations and column operations. You can stick on to row only, you can stick on to column operations only. But you know, mix and match will always reduce a lot of labor, a lot of time, and all those things. Right? Look, end of the day, I reduced this matrix, namely A, into a diagonal matrix. And this is my P inverse, this is my A, and this is my